Welcome to the deep dive. This is where we take, a bunch of source material, articles, books, notes.
And we really dig in.
Yeah, dig in deep to pull out the most important bits, the key insights.
The goal is to give you a kind of shortcut to getting properly informed, maybe with a few surprising things along the way.
And practical stuff, too, things that stick. Today, we're diving into a topic that's just, well, it's everywhere now, business analytics.
That's right. And our guide for this is excerpts from the book Business Analytics, The Science of Data-Driven Decision by Dr. U. Dinesh Kumar at IM Bangalore.
So our mission today, using only this source material, is to unpack the basics, the techniques, and really understand why analytics is such a big deal today. Why it's not just for, the specialists anymore.
Exactly. So whether you're maybe prepping for something specific or just trying to understand this field, or honestly, if you're just curious.
This deep dive should hit the spot. We'll explore what the source flags as most critical.
Okay, let's jump in. So first things first, what is business analytics, according to this source?
It definitely says it's more than just, crunching numbers.
Yeah, much more. It's framed as a whole body of knowledge. It mixes statistics, maths, operations, research.
And the newest stuff, too. AI, machine learning.
Machine learning, deep learning, plus the data tech that powers it all. Hadoop, Spark, TensorFlow, that kind of thing.
Okay, quite a toolbox. And the main goal?
Two things, really. Problem solving and decision making. Using all those tools to tackle business problems and make smarter choices backed by data.
Right. And here's a point the source really emphasizes, which I found interesting. Analytics isn't just a tool anymore. It's become a competitive strategy.
Absolutely spot on. It's not just something companies do on the side. They're building their core strategies around analytic insights.
And they list the big names, right? Amazon, Apple, Google.
Right. Google, Facebook, P&G, GE, all cited as using analytics strategically to find value, to get an edge.
That Amazon example is pretty stark, their recommender systems.
Driven by analytics, yeah.
They apparently drive a 35% increase in sales. That's huge.
It's a massive direct impact. And the source makes it clear it's not just the tech giants.
No.
Now, there's research mentioned that shows a pattern. Companies considered high performers, profit, shareholder returns, they're much more likely to be using analytics strategically day in, day out compared to lower performers.
So the bottom line for you listening is, getting your head around analytics isn't just for data scientists. It's fundamental to understanding how modern companies compete and how decisions actually get made. It's like the language of modern business.
Okay, so before you can analyze anything, you need the raw material data.
Right.
And the source starts with the basics.
Yeah.
Population versus sample.
Population being everyone, sample being a smaller group.
Exactly. And you usually work with samples because studying everyone is often, impossible or way too costly.
And this seems crucial, getting the sample wrong is a big problem.
A huge problem. The source is really clear. Bad sampling leads to bias.
And bias leads to
wrong conclusions. Simple as that.
They use that famous example, don't they? The 1936 election poll.
Oh, yeah, the Literary Digest poll. Classic cautionary tale. They pulled millions, like 2.4 million responses from 10 million surveys sent out.
A massive number.
Gigantic.
Yeah.
And they still got the result completely wrong. Predicted Landon would beat Roosevelt.
Oops. But Gallup got it right?
Gallup got it right with only 50,000 samples.
How?
Because Gallup focused on how he sampled, getting a representative group. Literary Digest used phone directories, magazine lists in 1936 that skewed heavily towards wealthier people who leaned Republican. Massive sampling bias.
Plus, probably only certain types of people bothered mailing the ballot back.
Exactly. Non-response bias, too. So the lesson isn't about size. It's about the method. Getting a sample that actually reflects the population.
Okay, method over size. Got it. Yeah. Now, data itself, it comes in different types, different scales. The source mentions the interval scale.
Right. This is for things where the difference between values matters, but the ratio doesn't, and 0 is arbitrary.
Like temperature in Celsius.
Perfect example. 40 degrees is 20 degrees hotter than 20 degrees. The difference is meaningful.
But 40 isn't twice as hot as 20 in a meaningful physical sense.
Exactly. And 0 Celsius doesn't mean no temperature. IQ scores, GPA, similar idea. Meaningful intervals, but no true 0, and ratios aren't meaningful.
Okay. So you've got your data, hopefully well sampled. First step is just describing it.
Descriptive analytics, yeah. Basic stuff we mostly know: mean, median, mode, finding the center.
The source seems more interested in variation.
Definitely. It says understanding variability is a primary goal in analytics.
Why is that so important? More than just finding the average.
Well, partly it helps spot outliers, sure, but critically, for building models, variation is information.
How so?
Think about it. If a variable barely changes across your data, say everyone in your study is almost exactly the same age, then age probably isn't going to be a very good predictor of, well, anything else.
Ah, I see. Low variability means low predictive power.
Pretty much. So understanding variation helps you pick which variables might actually be useful for your model.
And even simple descriptions can give real insights, right? Like the Walmart example.
Yeah, noticing Pop-Tart sales spiked before hurricanes. That's just observing variability in sales data and connecting it to an event.
Or just seeing how different customer groups shop differently.
Exactly, pure descriptive insights.
Visualizing helps here too.
No?
Histograms.
Yeah, showing frequency distributions. The source uses Bollywood movies, budgets, and box office. You can see the skew, see most movies cluster here, but then boom, there's an outlier like PK way out there.
Makes the pattern obvious. Ogive curves are mentioned too.
Briefly, yeah. Cumulative histograms, basically.
Mm-hmm.
Shows the running total.
Okay, now here's a really neat connection the source makes, linking this descriptive stuff directly to feature engineering.
Ah, yes, the DSRI example, Days Sales to Receivables Index.
Used for fraud detection.
Correct. It's a financial ratio. A high value, over 1:1, can indicate someone's cooking the books, like recognizing revenue too early.
So how does visualization help here?
Well, the source describes plotting the DSRI values for companies later found to be manipulating earnings versus non-manipulators.
What did it look like?
For the non-manipulators, DSRI was, relatively stable. But for the manipulators, you saw these spikes, often pushing way above 1, especially above 1.2.
Ah, so the chart screamed, look here.
Precisely. That visual insight immediately suggests maybe the exact DSRI isn't the key, maybe it's just whether it's high, like over 1.2.
So you create a new feature.
Exactly. You engineer a new feature for your fraud model, simple binary variable. Is DSRI equals 1.2? Yes or no? That insight came directly from describing and visualizing the data.
That's clever, using basic description to improve sophisticated models.
That's the power of it. Okay, so analytics often deals with unknowns.
Right.
Uncertainty.
Which means we need to talk about probability.
Foundational stuff.
Yeah.
The source covers the axioms probabilities between 0 and 1, all outcomes sum to 1, add probabilities for mutually exclusive events. The basics.
And the idea of independent events.
Crucial. One event's outcome doesn't affect the other, like a coin toss or the cricket toss example used. Winning the last one doesn't change the odds for the next.
But you can't just assume things are independent if they aren't.
Absolutely not. The source mentions the People v. Collins case, a legal case where misapplying probability, assuming independence incorrectly, led to major problems.
Okay, so be careful with independence. What about practical tools? Association rule mining.
Yeah, this is used a lot in retail. Recommendations. Metrics like support, confidence, and especially lift.
Lift tells you how associated things are.
Essentially, yes.
Yeah.
If the lift value is greater than 1, it means seeing item A makes seeing item B more likely than you'd expect if they were independent. They might be complementary people who buy X, often buy Y too.
And if lift is 1?
They're independent. If it's less than 1, they might be substitutes. Buying X makes you less likely to buy Y. Super useful for shelf placement, bundles, recommendations. The source mentions analyzing movie purchases and feedback too.
Got it. Probability also involves random variables, discrete versus continuous.
Simple distinction. Discrete variables are things you can count. Number of returns, customer churn, yes, son. Sentiment score, 1 to 5. Finite or countable outcomes.
Continuous can be any value in a range.
Right. Height, weight, time, temperature. Infinitely many possible values within a given range.
The source mentions specific distributions, too. Binomial.
Yeah, binomial's handy for situations with a fixed number of trials and 2 outcomes. Like, out of 20 job offers sent, how many will be accepted? You have n trials, 20 offers, and probability of success, acceptance.
And Poisson.
Poisson is for counting events over a fixed interval of time or space. Number of calls to a help desk per hour, number of defects per square meter of fabric. Useful for modeling arrival rates or occurrences. Some distributions even have a memoryless property mentioned, meaning the past doesn't influence the future probability.
Okay, so we have data, probability. Now we want to make claims about the bigger picture based on our sample. Hypothesis testing.
Exactly. This is the formal process for using sample data to test a theory about the population.
You start with 2 hypotheses, null and alternative.
Yep. The null hypothesis, 8-0, is usually the boring one, no effect, no difference, status quo. The alternative, age A, is what you're actually trying to find evidence for.
But you can make mistakes. Type I and type 2 errors.
Right. Type I error is rejecting H0 when it's actually true, a false alarm. The significance level, alpha, usually set at 0.05 or 5%, controls the risk of this error.
And type 2.
Failing to reject H0 when it's false, missing a real effect, that's beta. There's often a trade-off.
So how does a test actually work?
You calculate a test statistic from your sample data, like a t-score or a chi-square value. Then you see how likely that statistic is if the null hypothesis were true. This gives you the p-value.
And if the p-value is small?
Smaller than your chosen alpha, like 0.05, it means your result is pretty unlikely under the null hypothesis. So you reject H0 and say you have evidence for the alternative, HA.
Okay. Common applications mentioned. Comparing two group averages.
That's the t-test. Or seeing if categorical variables are related, like customer segment and churn status, using the chi-square test of independence.
And checking if your data fits a specific distribution.
Chi-square goodness of fit. The source uses Captain Cook's food survey example. Did the sailors' preferences match what was expected? It notes the rule about needing enough expected counts per category for the test to be valid.
Right. Now, here's that common pitfall the source points out. What if you want to compare means of, say, 3 or 4 groups?
Yeah, the immediate temptation is just run t-tests between every pair of groups, right? Group AVSB, AVSC, BVSC.
Sounds logical, but wrong.
Very wrong, according to the source. Doing all those separate tests dramatically inflates your overall chance of getting a false positive error.
Ah, because each test has a 5% chance of error and doing lots of them adds up.
Precisely. Your family-wise error rate skyrockets way above 5%. You're likely to find a significant difference just by luck.
So what's the right way?
ANOVA, analysis of variance. It's designed specifically to compare means across 3 or more groups all at once, keeping that overall error rate under control.
How does it work without doing pairwise tests?
It cleverly compares the variability between the group means to the variability within each group. If the means are far apart relative to the spread within the groups, the F-test statistic will be large, suggesting a significant difference somewhere among the groups.
Examples given were like price discounts on sales.
Yep, testing if different discount levels, say 10%, 20%, 30%, lead to significantly different average sales. Or if NBA specialization impacts average starting salary across multiple specializations.
So hypothesis testing is really about rigor. It's the formal way analytics decides if a pattern you see in your sample is likely real or just random noise.
Exactly. Like in that WSCS case study mentioned, Jack believed deals closed better in Africa than the UK. Hypothesis testing is how you'd formally check that belief using data, not just gut feel.
Okay, moving on to finding relationships between variables. First, big warning.
Correlation does not imply causation. Worth saying again.
Definitely. Correlation just measures how strongly things move together and in what direction. Pearson correlation is mentioned for.
For linear relationships between two continuous variables, like maybe called duration and customer age.
Then we get to simple linear regression, SLR.
Right, using one variable, x, to predict another variable, y. Finding that best fitting straight line, y equals 0 plus 6 mmx plus egg, usually using ordinary least squares, OLS.
And the source mentioned the origin of the term regression.
Yeah, from Sir Francis Galton studying heights. He noticed children of very tall or very short parents tended to be closer to the average height. Their heights regressed towards the mean. Kind of a neat historical note.
Regression is used everywhere in business, right?
Oh, constantly. The source gives examples like setting prices based on demand factors, predicting banking non-performing asset rates based on unemployment, or that DDAD hospital case predicting treatment costs from patient weight.
But building the model is only half the story. Validation is key. R-square comes up first.
R-square tells you what percentage of the variation in Y your model explains using X. Useful, but
big BUT coming.
Huge BUT. The source gives a stark warning about spurious regression. You can find variables that have an incredibly high R-square, like 0.99, suggesting a near-perfect fit.
But the relationship is complete nonsense.
Total nonsense. The example was UK helium poisoning deaths and the number of Facebook users. High correlation, high R-square, absolutely zero logical connection.
So rule 1, R-square isn't enough. The relationship has to make sense.
Absolutely critical. You need domain knowledge, common sense. Beyond that, other checks include, are the coefficients, 0, 0, BOCO, statistically significant, usually checked with t-tests.
Does the overall model explain significant variance?
That's the NOVF test for the regression model. And then, crucially, you need to look at the residuals, the errors, the difference between the actual Y and your predicted Y.
What are you looking for in the residuals?
You're checking the model's assumptions. Are the errors random, centered around zero? Do they have constant variance homoscedasticity?
What if they don't? Like that funnel shape.
That funnel shape in a residual plot is a classic sign of heteroscedasticity. The error variance changes as the predicted value changes. That violates an assumption. You also check if errors are normally distributed, and if there are patterns suggesting you used the wrong model form, maybe you needed a curve instead of a line.
Tools like Cook's distance help find influential outliers, too.
Yep, observations that are having a disproportionately large effect on your regression line. Need to investigate those.
Okay, so SLR is one predictor. More realistically, you use multiple linear regression, MLR.
Much more common, yes.
Yeah.
Using several x variables, x1, x2, x3, to predict y.
Which introduces new challenges, especially if you have tons of potential predictors.
Right. Variable selection becomes key. How do you pick the most important ones? You often want a simpler model, not one with hundreds of variables if you can avoid it.
MLR also needs ways to handle categorical predictors, like region or product type.
That's where dummy variables come in. You create binary O1 variables to represent the different categories.
And interaction terms become important.
Very important. An interaction term, like x1, x2, allows the effect of one predictor, x1 on y, to depend on the level of another predictor, x2.
The source had that interesting MBA salary example.
Yeah, where an interaction between being an engineering student and their marks suggested that for engineers, salary actually decreased as marks increased.
That sounds completely wrong.
It's definitely counterintuitive, but the interaction term revealed it, prompting a closer look. Maybe engineers with top marks went into different, initially lower-paying fields, or maybe there's something else going on. It shows how interactions can uncover complex realities.
Another big challenge in MLR mentioned is multicollinearity.
Yes. This happens when your predictor variables, the x's, are highly correlated with each other.
So they're kind of measuring the same underlying thing.
Pretty much.
Yeah.
And it causes problems for the model. It makes the coefficient estimates unstable and unreliable. Hard to know the true individual impact of each correlated predictor.
So lots to consider with regression. It's powerful, but you need to build it carefully and validate it thoroughly.
Okay, let's switch gears a bit. We've talked about predicting numerical values with regression. What about predicting categories?
Classification.
Exactly. And a primary tool here is logistic regression, especially for binary classification predicting one of two outcomes. Yes, no, no churn, fraud, no fraud.
How does it work? It doesn't predict 0 or 1 directly.
No, it predicts the probability of belonging to one of the classes, usually coded as 1, the positive class. It uses a logistic function, that S-shaped curve, to squeeze the output between 0 and 1.
The source used the Challenger disaster example.
Yes, tragically relevant. Predicting the probability of O-ring failure based on launch temperature. Lower temperatures increase the predicted probability of failure.
Evaluating these models is different too, right? Not just R-square.
Totally different. You use a classification table, sometimes called a confusion matrix. It shows how many you got right, true positives, true negatives, and wrong, false positives, false negatives.
And from that table, you get metrics like accuracy, sensitivity, specificity.
Right. Overall accuracy is just the total correct predictions divided by the total. Sensitivity is how well you identify the actual positive cases, true positive rate. Specificity is how well you identify the actual negative cases, true negative rate.
And this leads to that really important point. The source makes the accuracy paradox.
This is key. Sometimes the model with the highest overall accuracy is not the best model for the job.
How can that be?
It depends on the costs of different errors. Think about medical diagnosis or fraud detection. Missing a positive case, a false negative failing to detect cancer, failing to detect fraud, might be vastly more costly than a false positive, saying someone has cancer when they don't, flagging a legit transaction as fraud.
So a model that's slightly less accurate overall, but much better at catching the crucial positive cases might be preferred.
Exactly. The Challenger example again. A model predicting failure, the critical positive case, might be better, even with lower overall accuracy if it rarely misses an actual failure. The source highlights AUC area under the ROC curve as a popular metric for evaluating binary classifiers because it considers the trade-off between sensitivity and specificity across all possible probability thresholds. It gives a more balanced view.
Okay, so accuracy isn't the whole story. What other classification methods are mentioned? Trees?
Classification trees, yes,
Okay.
like C-Canade. These build rules in a flowchart structure. They split the data reputedly based on the predictor variables that best separate the classes, using statistical tests like chi-square or F-tests to decide the splits.
More intuitive, maybe, like a
Yeah,
set of if-then rules.
exactly. The ScaleWorks case study, as mentioned, predicting if a job candidate will accept an offer but then not join Renege. The tree might create rules like, if offer acceptance time X days and offered salary Y, then probability of Renege is Z%.
And then there's forecasting predicting the future based on past time series data.
Essential for business planning. The source mentions simpler methods like moving average and exponential smoothing.
Holt winters for seasonality.
Right. Single, double for trend, and triple Holt winters for trends and seasonality. And then more advanced models like ARIMA, all designed to capture patterns in data over time and project them forward.
The L&T spare parts case study sounds like a tough forecasting challenge.
Huge challenge. Forecasting demand for over 20,000 different spare parts, many with complex seasonality and low volumes. Need sophisticated approaches.
So classification and forecasting power, things like spam filters, credit scoring, demand plans.
All around us. The Shibum housing case study is another great example using classification models for loan application scoring. This allowed them to assess risk for people without traditional credit histories, opening up access to finance more efficiently than purely manual methods.
Okay, so we've predicted what might happen. The final step is prescribing what to do about it.
That's prescriptive analytics, moving from prediction to optimal action. This often involves techniques from operations research, or OR.
Linear programming, LP, is a big one.
A cornerstone of OR-LP finds the absolute best way, maximum profit, minimum cost, to allocate limited resources, given a set of constraints.
How does it find the best solution?
Mathematically, the optimal solution to an LP problem always occurs at one of the corner points of the feasible region, the space defined by your constraints. The algorithm efficiently searches these corners.
The perfume blending example illustrates this.
Perfectly. Deciding how much of each perfume to produce to maximize total profit, given limits on raw ingredients, machine time, etc., LP finds the optimal production mix.
And it gives you more than just the answer. Shadow prices.
Right. Sensitivity analysis is key. The shadow price tells you how much your objective, PG, profit, would improve if you could get one more unit of a scarce resource, like one more hour of machine time. Very valuable for decision making.
What if you have multiple goals, not just one?
That's where goal programming comes in, mentioned briefly. It tries to find a solution that comes as close as possible to achieving several potentially conflicting goals, like the Miss Moneypenny example, trying to balance profit, product attractiveness, and using limited shelf space effectively.
This prescriptive stuff seems incredibly powerful for making concrete business decisions.
Absolutely. The WSS Retail Markdown Optimization case study is a fantastic real-world example.
What did they do?
First, they used clustering, another analytics technique, to group stores with similar sales patterns. Then, they used optimization, likely LP or similar, to determine the optimal markdown percentage for each group of stores during clearance sales to maximize overall revenue while clearing inventory. Data driving the discount strategy.
Very smart. Any other advanced topics touched upon?
Just briefly, Markov chains were mentioned for modeling transitions between different states over time, like customers moving from active to inactive to churn. The flip card example was cited.
And ensemble methods, combining models.
Yeah, like random forest, which uses a technique called bagging. The idea is that combining predictions from many different models, often decision trees, usually results in a more accurate and robust prediction than any single model alone.
The IPL player pricing study used this.
Apparently so. Using various player statistics and performance factors within an ensemble model to predict auction prices shows how these advanced methods tackle complex prediction problems.
Wow. Okay, so we've really covered a lot of ground here, all drawing from the source material on business analytics.
We really have, from the basic need for good data and description,
through probability, hypothesis testing for making solid inferences,
finding relationships with correlation and regression, making predictions with classification and forecasting,
and finally, guiding decisions with optimization. It's quite a journey.
It shows analytics is this integrated, data-driven approach. It's used everywhere to solve problems, make decisions, and, gain that competitive edge.
And it's all built on these fundamental principles of stats and math, even the complex AI stuff.
Definitely. The source material gives a solid overview of that landscape.
So maybe a final thought for you listening. As you go about your day, think about all the data flying around at work, online, in the news.
What questions could you ask about it?
Yeah, what if you started thinking about variability? Or looked for correlations? Or even just framed a question as a hypothesis you could potentially test.
How might trying to predict something, even informally, change how you see a situation? What decisions, maybe even personal ones, could be sharpened up a bit with a more data-informed perspective?
Something to chew on. The power of analytics isn't just for big companies.
It's a powerful way of thinking.
Well, thanks for joining us on this deep dive into business analytics.
Hope you found it insightful.